Yeah,
Okay.
we can see.
Hi, everyone. My name is Mengyuan Xiao, a third-year PhD student from CS Berkeley and Nanjing University. Firstly, thanks organizers for having me here. Today, I'm going to talk about the starburst galaxies in the cluster at redshift 2.5, and we are studying their gas kinematics and try to answer what mechanism triggers the starburst in this cluster. As we've already know, the starburst galaxies in the local universe, they are mainly lugs and U-lugs, and their starburst is mostly triggered by gas-rich major merger. And in the high Z universe, actually, it's not so clear. Most starbursts at high Z universe are mergers, interactions, and irregular galaxies. And here we show some examples from the recent work showing the ubiquity of starburst galaxies in massive galaxy cluster progenitors. As it's shown in the top left panel, you can see the redshift 4.3 protocluster, and in the middle one is redshift 4 protocluster, and the right is 2.5 cluster. They all have high star formation rate in the central region. The SFR is about 3,000, from 3,000 to 6,000 solar mass per year, or even more. And also here I list some examples of protoclusters at redshift about 2, and also some dusty star-forming galaxies over densities at redshift higher than 4 with high star formation rate. In this presentation, I'm going to focus on this cluster. We call it CLJ1001. It is a massive starbursting X-ray cluster at redshift 2.5 from Taiwan 2016 paper. And it has halo mass about 10 to 14 solar mass. And in the central region, it contains about 11 massive galaxies with high star formation rate because most 9 of them are star-forming galaxies. And the short depletion time, about 200 million years. So this cluster has a collapsed cluster-sized halo and a predominant population of massive star-forming galaxies, which suggests it is in a rapid transformation from the protocluster to a mature cluster. And we've already do some studies about the environmental effect on the galaxy properties. For example, the gas fraction of the 14 cluster members showing the decreasing gas fraction towards the cluster core. Now we have 4 pointings of ALMA CO3 to 2 observations. We have detected more than 20 sources up to twice cluster viral radius with the high resolution about 0.3 arcsecond. Then we could start to do gas kinematic analysis of their individual galaxies. However, limited by the sensitivity, especially in our case, as we know, to do gas kinematic analysis, we need very high sensitivity for each resolved elements in galaxies. We finally have 4 brightest galaxies with enough signal-to-noise ratio larger than 10 of CO3 to 2 for us to do the follow-up work. Here we briefly named them Starburst 1, 2, and May sequence 1, 2 corresponding compared to the star-forming May sequence galaxies at the similar redshift. And then we can see their location. The left panel shows their sky distributions of member galaxies around the cluster center. The red circles mark the 4 starburst and May sequence galaxies, and the golden squares are cluster members with CO3 to 2 detections by ALMA. And the left is the phase space diagram. The 2 May sequence galaxies are located close to the cluster center, and the starburst close to the outer region, especially the starburst 1, it is close to the cluster viral radius. With the ALMA high resolution observations, we could trace the CO3 to 2 distributions of these 4 galaxies shown in contour here. As we see in the top right panel, it shows the CO spectra of starburst 1. It has clear double peak, implies the existence of a rotating gas disk. And here is a clearer picture. From the left to right, it shows the CO line intensity, the velocity field, and the velocity dispersion distributions. Normally, we call them moment 0, 1, and 2, and a PV diagram. From the moment 1 and PV diagram, we can see it have continuous shares, especially for these two starbursts. And moment 2 exhibit the central peak of the dispersion. It is consistent with the kinematics of rotating disks. Under the assumption of the regular rotating gas disks of these 4 galaxies, we can study their gas kinematics by using the software Galpax 3D. I will quickly show the results here. The 2 main parameters about the gas kinematics are gas rotating velocity and the velocity dispersion. The velocity dispersion describes gas turbulence, and the ratio of these 2 parameters is normally used to describe a gas disk is rotation dominated or random motion dominated. And the high V over sigma means it's rotation dominated. Here we see the V over sigma as a function of the redshift. The interesting point is, if you compare the 2 cluster starbursts to other star-forming galaxies from many different surveys and to some simulated galaxies in the field environment, especially compared to the field starburst galaxies at the similar redshift here, shown in blue triangles and orange markers. The 2 starburst galaxies have the V over sigma values more than 3 times higher than the median value of the field starburst galaxies. So which means their gas disks are obviously rotation dominated. And then let's move to the individual parameter. The gas velocity dispersion. Here is the sigma versus redshift. The galaxies at a higher redshift, their gas is more turbulent. It makes sense because the gas fraction is higher at higher redshift. There are many mechanisms can induce and maintain the gas turbulence, such as the gas accretion from the cosmological cold flows, stellar feedback in the form of supernovae and wind, and the gravitational disk instabilities and galaxy interactions. The interesting point is here. Let's only focus on the field environment. We compare the field starbursts, again, the blue triangles and orange makers, with the field star-forming galaxies here, green points. We can see the sigma value is slightly higher from the field starburst compared to the field star-forming. And then if we focus on the 2 starburst galaxies, we see their gas velocity dispersion is significantly low compared to other field starburst galaxies. The sigma is about 20 to 30 kilometers per second, and it is 2 to 3 times lower than the starburst in the field environment at the similar redshift. So now we've already know these 2 cluster starbursts have rotating gas disks, and their velocity dispersion is low and have high Vmax. This is, I didn't show, but it is high, but it's not significantly different from other field starbursts. And the last information is the high gas content. It is about 0.7. Then we could try to answer the question, what mechanism triggers the starburst? We calculate the 2 molecule value according to the previous informations. The 2 molecule value is used to describe a gas disk is stable or not. And then we found from this figure, 2 starburst galaxies in red have low values. So now we can say the most likely mechanism of causing their starburst is the gravitational instabilities of gas disks. That is to say, the gas disk is unstable, which is easily collapsed to trigger the starburst. Here is our main result. We found the two starburst galaxies have dynamically cooled gas disk, and there is no clear evidence of gas-rich major mergers. And the starburst is mainly caused by the gravitational unstable. Then let's go to deeper. What mechanism makes gas disk to be unstable? Is it because of the low velocity dispersion? But what mechanism caused the low velocity dispersion and also caused the high gas fraction and Vmax? There is a recent simulation work from the Kashmir this year, which are consistent with our results. Briefly, to build up a rotating gas disk as in our starburst galaxies, we need two conditions. One is the coplanar and co-rotating cold gas accretion. It can help us to rapidly build the gas disk and aid angular momentum and increase the V over sigma. It is consistent with our rotating disk with high V over sigma, low sigma value, and our galaxy size is about 2 kilopascal in radius. And the second one is the galaxy need to be massive because the massive galaxies have low gas merger rate compared to the orbital time, which can help the cold gas disks survive. The period will not be too long. Finally, the disk instabilities, violent feedback, and mergers will destroy those disks and make the gas turbulence again. And this is my last slide. I'm going to show some other observations. It also shows the existence of the massive rotation dominated disk at a higher redshift larger than 4. Most galaxies are also starbursts, but we don't know yet their environmental information. Our work is the first time that we see the surprised gas velocity dispersion in starburst galaxies in a dense environment. However, the effect of the environment on the dispersion of the gas disk is still an open question. And here is the conclusion. Thank you.